Welcome to our 5-3 Introduction to Periodic Trends on the Periodic Table of Elements. In 5-3, we're going to be doing a simulation, really a discovery in the trends of both atomic radius and ionization energy on the Periodic Table of Elements. Taking a look here at our lab write-up on 5-3, where you'll be recording everything that you're asked to record as we do this investigation. We'll see that the first part 1, is background information that you'll need in order to understand atomic radius and ionization energy. So this is our pre-lab stuff. You'll need to click right here on background vocabulary. When you click on background vocabulary, it'll take you to some information regarding atomic radius and what periodic trends are and so forth. When you go to that particular site, you'll use the information on that site to fill in the gray blanks right here on questions 1, 2, 3, 4, and 5. So all of those gray blanks you'll fill in from clicking on background vocabulary. Then we get to the two big terms at hand for today's investigation. One of them is atomic radius. Click on the definition of atomic radius and complete that definition in this gray box here. Atomic radius is, and you'll go ahead and complete the definition there. And you'll do the same for ionization energy. Click on the definition for ionization energy here. Ionization energy, also called ionization energy, that's the way the British spell it, is the minimum amount of what? You're going to complete the definition. And then there's an equation also listed on the definition of ionization energy. Complete what goes in the gray box there by looking at the equation they use to represent the concept of ionization energy. After completing the background information, you're ready to begin the investigation. Click on Lab, Periodic Trends, Atomic Radii, and Ionic Radii. So we'll click on that, and it'll take us to the simulation right here, which is really an investigation, and we'll see a periodic table. This is the periodic table of elements. But what this periodic table of elements will allow you to do is to compare the ionization energy and atomic radii of whatever two elements you are asked to compare. So let's say, for instance, I'm going to be comparing maybe potassium and radon, which you're not going to be comparing those two. That's why I picked those. We'll look down here. They did a drawing of potassium, a diagram of potassium. The 19 here is the atomic number of potassium. 2 electrons on the first, 8, 8, and then 1, for a total of 19 electrons. And they're doing Bohr's model here, obviously, which is an easy way to represent the electrons. Then we have radon. And we notice radon's Bohr diagram is smaller than potassium's. And we look down here, that's because the atomic radii of radon, the atomic radius of radon is 120 picometers. Potassium is 243. So when we look back at our lab, when we look back on the lab report, you're going to be comparing, like the first ones we're comparing are hydrogen and helium. You'll write down their radii, and you'll write down their ionization energies. Again, where do we find those? Right here underneath the diagrams, ionization energy and atomic radius. Now, how are we going to be comparing these? We're wanting to see if there's a trend on the periodic table of elements. The two trends we want to look at is there a trend or pattern for atomic radii as we go across a period, left to right, also called an energy level, also called a shell, left to right, the horizontal rows. We want to see if there are trends regarding the radii and the ionization energy. And then we're going to also look for group or family trends. So we're going to be looking vertical columns, which we call families or groups. Group 1, Group 2. Group 13 is boron and aluminum. 14, carbon and nitrogen. 15, or carbon and silicon. 15, nitrogen and phosphorus. 16, oxygen. 17 are the halogens, fluorine, chlorine, bromine, iodine. And 18, noble gases. You're like, why did we go from Group 2 all the way to 13? Because Groups 3 through 12 are right in here. These are the transition metals. We're not going to be looking at transition metals. The only ones you compare are the ones that are in green. After doing a comparison, you reset with the reset button right there. Click that reset button, and then you can pick 2 more to compare. So our comparisons are going to be left to right, horizontal rows, and top, which we call periods, levels, or shells, and then vertical columns. So the first comparisons we're doing are the horizontal rows, left to right. First row, you're going to compare hydrogen and helium. Then you need to gather information on lithium and carbon and reset it. Then you can do oxygen and neon and reset it. We're going to do the 6 out of the 7 periods that are there for us. Notice that the seventh period, they really do not have access to on this thing. The 7th period is the one that starts with francium. We're not going to be looking at the 7th period. So you're going to do the 6 periods. Then you're going to answer some questions on atomic radii trends, ionization energy trends. Then you're going to tell us, did you find the pattern by filling in the gray boxes with increases or decreases? And then we're going to look at the periodic trends of the groups or families. Group 1, Group 2, 13, 14, 15, all the way up to 18. Here you're going to do taking a look at hydrogen and lithium. And then you're going to be comparing potassium and cesium. Then you're going to be comparing magnesium and calcium in Group 2, along with strontium and barium in Group 2 or Family 2. Oh, wherever there's black, that means there's none there to do. So we're not going to be comparing every element on the periodic table that they give us. We're just going to be doing enough so that you can make some determination if there's a pattern. So on part 3 of the lab here, on that simulation, we're going to be looking at what you notice are the trends for the vertical columns, which we again call periods or groups. The questions you'll find right here. Did you notice any trends for atomic radius or radii and ionization energy? Radius is singular, radii is plural. And then we go on to the next part of the lab. Well, you have a question here on this page, increase or decrease. There you're making a kind of summary or conclusion to what you found with regards to the trends, patterns, or periodicity within the columns. Then we're going to look at size of cations. Ionization energy, we're going to find out has something to do with energy required to remove electrons. So now we're going to look to see what happens when we remove electrons. How do we do that on the site? Well, you come right here. I'm going to choose, for instance, strontium. And if I want to know, is strontium, well, let me make sure we're not doing strontium. Oh, yeah, we are doing strontium right here, so I don't want to do it now as our example. Let's say we're doing, I better reset it. Let's say we want to look at what happens to magnesium when we take electrons off. I click, there's magnesium. Ionization energy is there. Atomic radius is there. But now I want to make an ion. So I'm going to click on one of these electrons and drag it off to the side. I pulled one electron off. What happens when I pulled one electron off? Now I'm going to, and as I pull one electron off, it says this ion is not stable. So I need to remove more. So I'm going to pull another one off. And as I pull another one off, it will then tell me what the radius is of the ion. So I have the original radius of the atom right here. I have the radius of the ion right there. And I would record it radius of the atom, radius of the ion underneath there. And we want to see what happens to the size of an atom when we remove electrons. And that's what the questions are that follow. Then it wants you to try to remove electrons from oxygen. Explain why you can or why you can't. And then we move on to part 5. Part 5, we're going to be looking at the graphs of both atomic radii. In part 5, we're going to look at the graphs of atomic radii. And then in part 6, we're going to look at the graphs of ionization energy. These graphs plot the ionization energy and atomic radii for all the elements on the periodic table. Those graphs are also represented right here. So if I want to look at a graph, I click on Go to Graphs. And you're like, where did the graph go? You have to scroll back up to find the graph. Here's the graph of the atomic radius of all the elements. The one we were just looking at is magnesium. It is right there. This graph for atomic radius is already copied for you right here. This is the atomic radius graph. Some lines have been added in for you on this graph and some element markers or labels so that you can see what we're looking at on the graph. So here's a graph, and there's going to be some questions on the atomic radii underneath that graph right here. You're going to have to explain why the graph slopes as it does when we're comparing what happens to the atomic radius through a group. Here's group 1, lithium, sodium, potassium, rubidium, and cesium, and a line's connected there. Here we're looking at group 18, Roman 8. That line is plotted for you right there. They're asking you, why is that line going sloped up? Then we're going to look at a graph which shows the periods. First period, second period, third period, fourth period, fifth period, sixth period. Those are the horizontal rows. So lithium through neon is the second row. It says here, second period. It is the second row on the periodic table of elements. So if we go back, if I want to close the graph, I can close the graph right up here. It'll take me back to the periodic table of elements. Second row is lithium through neon, second period. So they're going to be asking you questions about the trends that we see in the second period. They're going to do the same for the ionization energy graph. They're going to look at groups first, and then they're going to look at the graph for the periods second. How do we get to a graph for ionization energy? Well, first we click right down here, go to graphs. The first graph, I have to scroll back up to it. This is the graph for atomic radius. It says it right here in the upper left. But if I want to get the ionization energy, I scroll down on this little drop-down menu and click on first ionization energy. There's magnesium. If we want to look at all of them, boom, there's the first ionization energy for all of them. What do they mean by first ionization energy? First ionization energy is the energy needed to rip off the first electron from an atom. Second ionization energy would be the energy required to take a second electron. Third ionization energy would be the energy required to remove a third electron. So you're going to have some questions then on atomic radii, on the graph for atomic radii, looking at periods and groups. And then you're going to have some for ionization energy, looking at periods and groups. And then we get to the last part of this little investigation or online lab or whatever you want to call it. How do they know what the atomic radii are for atoms? How can they find the radius of something so small? Click on this right here and it'll tell you how they determine experimentally the atomic radii. Now, you are not expected to understand how they did it, but just have a general idea that they're able to do it. And tell me 2 ways that they do it. Then how do they determine ionization energy? That's the last part of the lab. How do they find how much energy is required to remove an electron? Click on this little site here. It'll take you to some information regarding ionization energy. Find the paragraphs that you'll need to fill in the gray blanks here, showing me that you took a look at how they can experimentally determine ionization energy. This is our introduction to Unit 5, which is a continuation of understanding the periodic table of elements. In Unit 4, we dissected the periodic table of elements and saw how it represented quantum numbers. In Unit 5, we're going to take a look at trends on the periodic table of elements, beginning with atomic radii and ionization energy in this first investigation. Good luck.